in continuation to my previous lecture on Fibonacci method, today again I am going to cover another method that is a very well known method, that is a golden section method. That is again a region elimination technique. Now, with that I am starting today. Now, since this is again a region elimination technique, that is why in the method always the initial interval of uncertainty will be given to us, and based on that we have to find out the optimal solution. But there is one difference with the Fibonacci method, is that in the Fibonacci method we need to know how many experiments we are going to do, that we need to know beforehand. But here in the golden section method, that is not needed. We are expecting that we will do a large number of experiments, and based on that we will find out the optimal solution. Now, let A to B, the interval of uncertainty is given to us, and we do not know how many experiments we are going to do, but we will see when the convergence will reach, we will stop the iteration. Now, but the basic principle is based on just like the Fibonacci method, that we will find out 2 points in between which is equal distant from both the ends, and from there we will find out the optimal solution. This is the first point, that is the first approximation of the optimal solution, that is x1, and this is being calculated with the A plus 1 by gamma square L0. L0 is the initial interval of uncertainty, that is B minus A, and here one parameter we have introduced, that is gamma. Fibonacci method was based on the Fibonacci numbers, but golden section method is based on the parameter gamma. First point we will consider, that is x1, and the second point would be equal distance apart from the point B, that is B minus 1 by gamma square L naught. Okay. That is why we could see that the distance is from A to x1 is 1 by gamma square L naught, and the same distance x2 is from B is 1 by gamma square L naught. Okay. And this is the value. Since we are going to the next iteration with these values, that is why we are starting from A to B, we are going to the next experiment, that is why the naming is L2 star, just like your Fibonacci method. But here the question arises, what is the value for gamma, how really gamma will be calculated? That is a beautiful thing in golden section method. This is called the golden ratio. Gamma is the golden ratio, and that is a very nice property it has. Let me tell you the property of gamma first. Now, we know from the Fibonacci number that fn minus 1 plus fn minus 2 is equal to fn. That is, for the Fibonacci series, any number in the current position is the sum of the numbers in the previous two positions, we know. Okay. That is why if we do some simplification here by just dividing with fn minus 1, we could see that 1 plus this one. Okay. 1 plus fn minus 2 divided by fn minus 1 is equal to fn divided by n minus 1. What is n? N is the number of experiments we considered in the Fibonacci method. Now, as I said, in the golden section method, this n is not given to us. Okay. We will always depend on the convergence criteria. What is the convergence criteria? Whatever value we are getting in one iteration and whatever value we are getting in the previous iteration, the difference must be very small. Then we will say that the method has converged and we will stop there. That is the idea. Now, here I said that in golden section method we are thinking that the number of experiments would be infinite. That is why what we will consider, limit n tends to infinity fn by fn minus 1, and truly speaking this is the value for gamma, that is the golden ratio. But there is another significance of golden ratio as well. because this golden ratio has come, the architect, they are also using this golden ratio. That is the beauty of it, because it has been the Greek architect, they said that if we consider a room, if we design a room in such a way that is of rectangular form, and there are two sides of the room, one is D and another one is B. If we just consider D plus B divided by D is equal to D by B is equal to gamma, if we just design the room in by just considering this ratio, we will see that always the room will have a pleasing property, and this gamma value has come from there only. We have seen after this gamma has been associated with this optimization technique. Not only that, this gamma has been associated with the Fibonacci number in this way. Why did we say gamma is equal to limit n tends to infinity fn by fn minus 1? Because we know it is starting from f0. The value for f0 is 1, f1 is 1, f2 is 2, f3 is 3, f4 is 4, f5 is 7, oh sorry, this is 5, this is 8, f6 is 11, 13, f7 is 21, this way it is going. Okay. If we consider fn by fn minus 1, that is f1 divided by f0, take the ratio of it, this is 1. Take the ratio of f2 by f1, take the ratio of f3 by f2, again just you consider f4 by f3, f8 by f7, f7. If I just proceed in this way, we will see that this ratio will converge to the value of gamma. Now the question comes, what should be the value of gamma? This gamma value you can consider by considering this ratio only. If we just find out the ratio values from here, we will see that the value of gamma, the value is converging to a certain decimal point, and that is the value of the gamma. That is the beauty of it. But from here we can also find out the value for gamma as well. How really it is? From here, since if we just take the limit n tends to infinity in both the sides, then we will see that this is 1, the next term is 1 by gamma, because limit n tends to infinity fn minus 1 divided by fn minus 2 is equal to gamma, okay, and the right hand side would be again a gamma. Okay. If we just do some simplification, this will become a quadratic equation. What is that quadratic equation? The quadratic equation would be gamma square minus gamma minus 1 is equal to 0. Okay. Since this is a quadratic equation, we can get the value for just like a minus b plus minus root over b square minus 4ac divided by 2a. With that, if we just consider the value for positive value, we will see that the gamma value will come 1.618. Okay. And 1 by gamma rather will come 0.618. That is the beauty of it. Here also you will see the same thing. If we just consider the ratios of the Fibonacci numbers in this way, fn by fn minus 1, limit n tends to infinity, even you need not to wait for greater value of n, you will see after this only it will converge to 1.618. Okay, that is the beauty of gamma, and this gamma parameter we will consider in our golden section method. And what is the method altogether? Method is just like your Fibonacci method. We will consider the initial interval of uncertainty. We will consider 2 points that is equal distant apart from the end points. We will see the functional values in these 2 points. After that, we will consider the region elimination property. Since the function is unimodal, if we are going to find out the minimum of the function, then accordingly we will proceed. okay, but we will consider gamma value this value. I will show you the example in the next. Now you see the first solution x1, that is the L naught by gamma square distant apart from A, x2 is the same, and you have to manage the region, you have to consider the region by eliminating the region by using the unimodality property. Okay. That is why initially we are having 4 points A, x1, x2 and B. We will see the trend of the function. If we see that the function is not having the minimum value, there is no possibility to have the minimum value within x2 to B, then we will eliminate that region. We will consider the new interval of uncertainty as A to x2, and even if it is the other way, we will do the same thing. And once we are getting again another interval, we are getting 2 endpoints of that interval, again we will consider x3 star. What is the value for x3 star? That L3 star rather. L3 star, what is the value for that? That is L naught divided by gamma cube. And again we will take 2 points that would be equal distant apart from the new interval of uncertainty. And what is that equal distance? That is L naught divided by gamma cube, that is L3 star. Okay. We will get again 2 points within the endpoints. Again we will use the unimodality property, again we will just discard, eliminate a portion of the interval, and in this way we will proceed. How long we will go? As I said in the golden section method, number of experiment depends on the convergence criteria. That is why if we just proceed in this way, we will see at the jth experiment Lj star will be considered. That is the pattern of the golden section method, and we will take 2 points again, that is Lj star distant apart from both the ends. In this way we will proceed. Okay. That is the golden section method. That is why if we just calculate the length of the interval of uncertainty, initially it was L naught, because that is B minus A, that is given to us. We know the function is unimodal from between A to B. We know that property. Unimodal, if either this is it has a unique maximum or it has the unique minimum within that interval. That is the unimodality definition. And second interval of uncertainty, that would be L naught minus L2 star, because we have considered 2 points, that is L2 star distant apart from both the ends. After using the region elimination technique, one part will be eliminated. That is why the new interval of uncertainty would be L naught minus L2 star, that will be L2. In this way we will proceed, and jth would be Lj minus 1 minus Lj star. Okay. And if we just see the pattern, the values are coming like this: L naught by gamma, but L2 star is your L naught divided by gamma square. Okay. And L3 would be L naught by gamma square. In this way we will proceed, and in the jth experiment L naught by gamma to the power j minus 1, but Lj star is equal to L naught divided by gamma to the power j. I showed you in the previous. That is why if I ask you what should be the length of the nth interval of uncertainty, very easily you can say that must be Ln, and the value of Ln you can calculate. Okay. That way we will proceed in the golden section method. Other than this, nothing is there in this method, and we will just see the convergence. Now let us try to find out the minimization of the function e to the power x plus 10 into x square e to the power minus x. If we just look at the functional description, function is very complicated in nature, because there are involvement of exponential function e to the power x, e to the power minus x, and if we just want to apply your classical optimization technique, maybe little bit difficult to get the values very easily, but we know that the function is unimodal within -1 and 1. Let us apply the golden section method here. You can apply any other region elimination technique as I explained you before. Okay? Let us apply golden section method here. How to do it? We will consider A as -1, B as 1, and we will consider 2 points x1 and x2, that is L2 start distant apart from -1 and 1. In this way we will proceed, and we will consider that we will see that the -1, then the next point is -0.23604 and the other point is 0.23604, okay, and the next point is 1 given to us. Then what is L2 star here? Certainly the value must be 0.23604. Okay. Now we will see the functional values here. What is the trend of functional values? If we see that the functional value is coming 27, okay, 0.5507, next one is 1.49, next one is 1.7, and next is 6.3. All right. We must see that there is no minimum between A to x1. All right. That is why we are proceeding to the next by considering x1 as the left hand new interval of uncertainty and 1 as the another right part of the interval of uncertainty. Again we will repeat the process. We will again find out 2 points in between, that is L3 distance apart from x1 and b, and what is the value of L3 star? You know that L3 star distant apart, and again we will find out the functional values, and from there we could see that between x3 and b there cannot have any minimum value. Okay? That is why we must exclude the point, exclude the region x3 to b. In this way we will proceed. Still we could see functional value is not converging. That is why we need to do further iterations for this problem. We are again eliminating a portion, and what I suggest to you, whatever values I am showing to you, these are the values I have already calculated before, but I should suggest to you, you do the calculations on your own. You may use simple, you can write a simple program, or you can use the Excel for calculating the values of these, and we can have different iterations this way. Could you see the functional values are converging somewhere? Okay. We will proceed further. I need not to explain again how really we are eliminating the region from here. We will proceed this way, and somewhere you see the functional values are converging to 1, because within this interval functional values are almost 1, 1.0, 0.97, 0.98. If you are happy with these values, then you can stop your iteration in at this point. You can say this is we have arrived to the convergence criteria has been satisfied, and what should be the optimal solution then? Optimal solution would be in between x6 and x7. Okay, that is your new interval of uncertainty. Take the middle point of that and declare that is your optimal solution. But one thing you must be clear, you should know that the nature of the function is if you consider the bigger interval, you are not confined with within -1 and 1. If you just proceed further -2 to 2, -10 to 10, the pattern of the function will be different. That is why I do not think this is the global minimum we are getting. We are only getting a local minimum point between -1 and 1. Now till now we have covered many region elimination techniques. Now the question must be coming to in your mind that what is the best method which method will be used so that we will get the optimal solution efficiently. What is the criteria for efficiency of optimality of the region elimination technique? That is, the number of experiments must be less. Okay, convergence should reach in very quickly, then only we can say that we have reached to the solution and this method is the best one. Let us try to compare that how many iterations really we need to get 10% accuracy of the optimal solution or the 5% accuracy of the optimal solution. Okay. Now, I am going to explain you that part in the next. That is why the solution has been declared x as a 0 and f x is equal to 0.98. Okay. Now, if we just see that different elimination techniques, we have covered the exhaustive search, dichotomous search, interval halving, Fibonacci method and golden section method. Let us compare these 5 methodologies. Now, in the initial interval of uncertainty, everywhere is L naught, then only we can compare L naught if this is same. Okay. If the initial interval of uncertainty, the value is increasing, then the situation will be different. If we have the same initial interval of uncertainty, just look at the final interval of uncertainty after the nth experiment. For exhaustive search, this is 2 into L naught by n plus 1 and the reduction ratio is 2 by n plus 1 if we do n number of experiments. Similarly, for the dichotomous search, we could see the reduction ratio is 1 by 2 to the power n by 2. For interval halving is half to the power n minus 1 by 2. For the Fibonacci method, we have seen that ln by L0 is 1 by Fn. We could find it out before because we considered ln is equal to f1 by Fn L naught, that is equal to L naught by Fn. That is why the reduction ratio, if we consider ln by L0, what is the ln is the nth interval of uncertainty, the length of the nth interval of uncertainty, L0 is the length of the initial interval of uncertainty. Reduction ratio means after reaching to the nth experiment, what is the ratio of ln by L0, okay, with respect to the initial. Now, that is 1 by n, and in the golden section method you must have seen that ln is equal to L naught divided by gamma to the power n minus 1, where ln star was L naught divided by gamma to the power n. But here the gamma value, you know, that is equal to 1.618 and 1 by gamma is equal to 0.618. That is why if we just calculate, we will see that this golden section method is having this one. Now, from here you can get some idea for what is the better reduction ratio. Reduction ratio, it means that how much we are eliminating in each iteration, how much length we are eliminating in each iteration, alright, that is the reduction ratio. That is why if we just see here, then we could see that somewhere Fibonacci method and the golden section method is almost same, but other methods, these are taking longer time to reach to the convergence. That means you need to have large number of experiments, very large number of experiments. Let us do another analysis where we will see that if we consider 10% accuracy by considering L naught as initial interval of uncertainty, how many experiments we need to do? If we consider 5% accuracy, what is the value? What is the number of experiments? Let us see. For exhaustive search, we have seen that the reduction ratio was 1 by n plus 1. That is why 10% accuracy means half into ln by L0 must be less than is equal to 10%, that is 10 by 100. Alright. That is why if we just calculate, we could see that the exhaustive search is taking more than 9 experiments. for 5% accuracy in more than 19 experiments you need to do. Dichotomous again 6 and 8, and interval having 7 and 9, but you see the Fibonacci, you need to have only 4 number of experiments to get the 10% accuracy, whereas to get the 5% accuracy you need to have more number of experiments, that is 6. But look at the golden section method, 5 and 5 in both the cases. That is why, as I said, it has been considered that Fibonacci method is the best method till date to do the region to implement the region elimination technique, because it has to do less number of experiments. Okay, another thing just I would like to point out here, you must have been seen, if I want to get the 10% exact value, that means, and another on the other hand we want to get the 5% accuracy, we could see the 10% accuracy, the interval is larger than the 5% accuracy, alright. That is why we need to do more number of experiments, though in the golden section method, that is just only because of mathematical calculation we could see the both the values are same, but it is not that will happen if I want to get that 1% accuracy, values may not be same. You can calculate how many number of experiments we need to do if we want to get 1% of accuracy. That is the task of yours, do it. Thank you for today.